Welcome to another video for organic chemistry. In this video we're going to be discussing Markovnikov's rule. Okay, so the following video is a result of Vladimir Markovnikov's observations with chemical reactions that he did. Okay, this was in 1869. So there are two ways to view Markovnikov's observations. Okay, so he did hundreds of chemical reactions and he noticed a pattern in some of the results that he was getting. And one of the ways, as I was mentioning, is looking at the hydrogen. So he was looking at how certain acids, acids that had halogens attached to it, and in our particular reaction we're going to be looking at hydrochloric acid. So we're going to be looking at hydrogen and the chlorine compound and how they combine with carbon chained molecules, and in this case we're talking about a propene. So again, we're focusing on the hydrogens. Hydrogen being placed in the vinyl position already bonded with the most hydrogens. And what that means is that we're paying attention at the hydrogen to see which carbon it prefers to bond with. Okay? So we're gonna isolate, we're gonna focus in on the carbons in our carbon chain molecule, and we're going to pay attention to how many hydrogens are attached to those carbons, and if the amount of hydrogens attached to those carbons determine where our hydrogen will bond. I know it probably sounds confusing how I'm saying it, and I hope the example that I use will actually clear up this first particular way of looking at it. Secondly, we're going to be looking at it in terms of the halogen itself, which is the chlorine for us. So in terms of the halogen being placed in the most substituted position. So we're looking at which particular carbon does the halogen prefer to bond itself with. Okay, so let's take a look at an example. We have a propene structure here. Okay, I want you to notice that double bond there. Okay, we have three carbons, two of them are double bonded. Now we have our hydrochloric acid. So we have our positive ion. Okay, so we know that there's a bond there, and then when it breaks up, our hydrogen and a halogen, we have a negatively charged chlorine and a positively charged ion, hydrogen. Okay, so again, like I mentioned before, let's take a look first at this hydrogen. Okay, which particular carbon does this hydrogen ion prefer to bond with? Will it bond with which vinylic group or which carbon? Okay, so when you say that term vinylic, that's just a fancy organic chemistry term, meaning which carbon does this hydrogen prefer, which vinylic group? Okay, so our double bond, and you'll notice that our double bond has two carbons attached to it. Okay? So there's a term that's used for determining which group this hydrogen, which vinylic group our hydrogen will bond with. Okay, so think of the term the rich get richer. So whichever carbon has the most hydrogens attached to it, that's the vinylic group that our hydrogen ion will choose to bond with. Okay? So again, I look at my two carbons where my double bond is, and I look, the rich get richer. So that means the one who has the most hydrogens will get the hydrogen ion. And as I mentioned before, our CH2, that's where our hydrogen will bond. And that CH2 will then become a CH3. Okay? So that's the first way of looking at it. Okay? Now, let's take a look at this from the perspective of the halogen itself, our chlorine. Okay, now, when that hydrogen bonds with our carbon, that creates a positive charge on one of our carbons, our middle carbon. Okay, so a carbocation forms. Okay, so that chlorine is going to prefer that chlorine, that carbon, because of the positive charge. So the negatively charged chlorine will be attracted to the positively charged carbon. So our nucleophile and our electrophile being the carbon, which loves electrons, and our nucleophile, which is our nucleus-loving chlorine, is going to be attached to the carbon. So they're going to make a perfect match. Okay, and keep in mind also that this is a second-degree carbocation, which is more stable than our first-degree carbocation. Okay, so our first-degree carbocation could be either ends of our carbon molecule, and preferably a halogen would rather bond to a 2-degree carbocation than a first-degree carbocation. And again, I have another video talking about carbocation, so please refer to that video if you can't quite remember what a carbocation is, which essentially is a carbon molecule, carbon atom with a positive charge. Okay, so our most stable form is the carbocation with a secondary carbocation with our positive charge in the middle carbon. So then our chlorine, our halogen, will bond with the most, it says submitted there, but it should say substituted carbon. So it will bond with the most substituted carbon. And all that means is that when I refer to a carbon being substituted, I'm referring to the amount of carbons that it's attached to itself. So if I look at my 3 carbons, the carbon that has the most other carbons attached to it is our middle carbon. Okay, because the carbons on the end only have 1 other carbon attached, but our carbon in the middle has 2 carbons attached on both sides, so it is the most substituted carbon. Okay, so that is why our chlorine will bond to that particular carbon. Now, something interesting happened when Markovnikov would do his reactions, because on occasion he would actually get a molecule that actually resembled this, where our chlorine would actually bond to an outer carbon instead of the inside carbon. This is what we would call an anti-Markovnikov addition. Okay, this is even though this particular reaction does occur, it is not a preferable reaction. And there were some experiments from other scientists when they would try to replicate his experiments or his results. They would find that they would actually get a majority of anti-Markovnikov additions as opposed to the halogen attaching itself to the middle carbon. And so they were wondering what it was, and some even speculated that it was the phases of the moon, that were causing these different anti-Markovnikov results. But as a result, actually as a result of further study, they just figured out that the level of impurities in the reaction was causing these anti-Markovnikov results. By impurities, I mean things like peroxides that were blended in by accident or something that would change the results. So the most preferred result is when the halogen would attach itself to the second degree carbocation or the carbon in the middle. That is the most preferred. Now again, anti-Markovnikovs would come out, maybe at a rate of like 10% or so. So they do happen, and again, it depends on the amount of impurities that we're in. And there's also other factors that are involved in impurities being, or anti-Markovnikov reactions happening, but we won't get into that just yet. I'll save that for a future video. Okay, well, that does our explanation of Markovnikov's rule. Thank you for listening. I hope this helped, and good luck in your studying.